Welcome dear learners. We are studying quantum chemistry and in this module we are discussing radial distribution function. The contents of this module include total wave function of hydrogen atom, quantum numbers namely principal azimuthal and magnetic quantum number denoted as N, L and M, the Swayam effect, the radial part of the wave function, radial probability distribution curves, angular part of the wave function and polar diagrams. First of all, the total wave function of hydrogen atom. The complete wave function for a hydrogen atom or a hydrogen-like system can be represented as psi NLM r theta phi equal to RNLR into YLM theta phi. And in this expression, it is clear that n having values from 1, 2, 3, etc. Later it is known as the principal quantum number. L can have values ranges from 0, 1, 2, 3, etc. up to n minus 1 called the azimuthal quantum number. M can have values from 0, plus or minus 1, plus or minus 2, etc. up to plus or minus L. And M is termed as the magnetic quantum number. It should be noted that YLM theta phi is known as angular part of the wave function. This part is known as angular part because YLM theta phi depends on two angular variables, namely the theta variable and the phi variable. This angular part is also called spherical harmonics. And previously we learned about spherical harmonics. And spherical harmonics or angular part of the wave function, YLM theta phi is equal to epsilon, that's a numerical constant, multiplied with under root 12 plus 1 L minus M factorial divided by 4 pi into L plus modulus of M factorial into PLM cos theta into e raised to im phi. Now, the complete wave function can be again splitted and represented like this. That is, psi NLM r theta phi equal to RNLR multiplied with the theta LM theta multiplied with the phi M phi. It is clear that RNLR is the radial part of the wave function, theta LM theta is the theta part and phi M phi represents the phi part. And the radial part depends on two quantum numbers, namely principal and azimuthal quantum number, that is N and L. The theta part depends on two quantum numbers L and M. And the phi part depends only on the magnetic quantum number M. We can put values corresponds to RNLR, theta LM theta and phi M phi in this equation to get the big equation like this. That is, psi NLM r theta phi is equal to under root 2z by ni0 cube into n minus L minus 1 factorial divided by 2n into n plus L factorial cube multiplied with e raised to minus zr by ni0 into 2zr by ni0 raised to L into summation k is equal to 0 to k is equal to n minus L minus 1 of minus 1 raised to k plus 1 n plus L factorial squared multiplied with 2zr by ni0 raised to k by n minus L minus 1 minus k factorial into 12 plus 1 plus k factorial into k factorial, again multiplied with under root 12 plus 1 L minus m factorial divided by 2 into L plus 1 factorial into PLM cos theta multiplied by under root 1 by 2 pi into e raised to im phi. This about the complete wave function of hydrogen atom or hydrogen-like system. Now, it is obvious from this equation that the total wave function contains three discrete terms They are n, l and m, and three continuous variables are theta and phi. That means in the Schrodinger wave equation, the solution to the Schrodinger wave equation contain three discrete variables n, l and m, and three continuous variables are theta and phi. In order to be a well-behaved function, we previously learned about the condition for a function to be well-behaved, like conditions are single-valued, continuous, normalized, finite. And in order for a function to be well-behaved, there are some conditions over the values of discrete variables that must be followed. That is, the values of n, l and m must have certain values, must have a certain finite values. Therefore, we can conclude that the principal quantum number n, azimuthal quantum number l and magnetic quantum numbers are obtained as a solution of Schrodinger wave equation of the hydrogen atom. That means we got these three quantum numbers from the solution of the Schrodinger wave equation for hydrogen atom. And it should be noted that the quantum number, spin quantum number, is not appeared anywhere else here in this solution of the Schrodinger wave equation. That we will separately deal in the coming schedules. Now, detailed about different quantum numbers. The first quantum number, principal quantum number or n. The principal quantum number is denoted by the symbol n and can have values from 1, 2, 3, etc. up to infinity. The label principal is allotted because valid values of L and M, that is azimuthal and magnetic quantum number, can be defined only after defining an acceptable value of n. That means, in order to set the values of L and M, we have to fix the value of n first. Then only we can move on to L and M. Hence, n is termed as the principal quantum number. Now, significance of the principal quantum number. The energy of an electron in hydrogen-like systems depends on principal quantum number n. The expression for energy is like this: En, energy depends on principal quantum number. En is equal to mu z square e raised to 4 divided by 2n square s cross square. That is, n depends on the energy of the hydrogen-like systems. Degeneracy in hydrogen-like systems. We know about the degeneracy. Degeneracy represents more than one possible arrangement with the same energy. For instance, we know the fact that p orbitals are triply degenerate. That means px, py and pz are three different arrangements with the same energy. So, degeneracy in hydrogen-like systems is also connected to the principal quantum number n. This is another significance of the principal quantum number n. Since the total number of wave function that can be written for a given value of n or n square, we can say that the degeneracy of any energy level is also n square. So, degeneracy of a particular energy level equal to n square. Degeneracy of the second energy level, E2 equal to 4, E3 equal to 9, like that. That means degeneracy is equal to n square, that is square of the principal quantum number. This is applicable to hydrogen and hydrogen-like systems. Moving on to next significance of principal quantum number. The maximum number of electrons present in unit cell is also related to the principal quantum number. Since two electrons can have the same set of principal, orbital and magnetic quantum numbers via opposite spins, the maximum number of electrons per unit cell or present in an orbital will be equal to 2n squared. That is, n is the principal quantum number. Now, The second quantum number, that is azimuthal quantum number. The azimuthal quantum number is denoted by the symbol L and can have values n minus 1, n minus 2, n minus 3, etc. up to 0. Or telling in the reverse order, L can have values ranging from 0, 1 to 3, etc. up to n minus 1. That is, n minus 1 is the highest value of azimuthal quantum number. The label azimuthal quantum number is also called as angular momentum quantum number. This is because the value of L also governs the orbital angular momentum of the electron. That is, angular momentum of an electron moving in an orbital. Now, the significance of azimuthal quantum number L. Orbital angular momentum of the electron can be determined from the value of L. The average value of angular momentum capital L is represented as volume integral psi NLM r theta phi L hat psi NLM r theta phi, where L hat represents the angular momentum operator, total angular momentum operator. On using the RHS, we can evaluate the average value of the angular momentum, and the average value we get as under root small l into L plus 1 h by 2 pi, where the small l represents azimuthal quantum number. Now, the second significance is number of subshells that are present in the main shell. The azimuthal quantum number can also be used to classify different quantum mechanical states on the basis of orbital angular momentum. That we know L is equal to 0 represents S subshell, L is equal to 1 represents P subshell, L is equal to 2D subshell, so on so. Now, the third significance, that is angular nodes in the atomic orbital. We know node is a region where the probability of finding an electron is equal to 0. The value of L, that is azimuthal quantum number, also controls the number of angular nodes that pass through the nucleus. An angular node or a planar node or a conical node is observed when the angular part of the wave function passes through 0 and changes its sign. Here these are p orbitals, and for p orbitals L is equal to 1 and L is same as number of angular node. Here at this portion the value of the wave function is equal to 0, and after that the sign of the wave function changes from minus to plus. And for the S subshell, that is for that L is equal to 0. This represents an S orbital, and for S orbital L is equal to 0. That means there is no angular node or planar node or conical node. Hence, number of angular nodes can be computed from the value of L. The third quantum number, that is magnetic quantum number or M or ML. It is represented as ML because magnetic quantum number has some connection with the azimuthal quantum number. Hence, we sometimes notated it as ML. The magnetic quantum number is denoted by the symbol M and can have values from plus L to minus L including 0. That is, M can have a total of 2L plus 1 values. Values ranges from minus L through 0 to plus L. Let L is equal to 2. That represents the D subshell. For that, M is equal to minus 2, minus 1, 0, plus 1 and plus 2. That is, from minus 2 to plus 2, all values are there. So, that represents the magnetic quantum number. The label magnetic quantum number arises because M affects the energy of the electron in an externally applied magnetic field. In the absence of such a magnetic field, all spherical harmonics corresponding to the different arbitrary values of M will be equivalent. So, whenever you are applying an external magnetic field, that degeneracy lifted and we will get different possible arrangements. Now, the significance of the magnetic quantum number. The first and most important significance is the orientation of orbital angular momentum. The Z component of the angular momentum is determined completely by M through Lz equal to Ms cross. Also, Lz equal to L cos theta. Capital L represents total angular momentum. Lz represents component of angular momentum along the Z direction. And we also know total angular momentum L is equal to under root L into L plus 1 S cross. These three relations are very, very important. Lz is equal to Ms cross, Lz is equal to L cos theta, and L is equal to under root small l into L plus 1 S cross. For example, let L is equal to 1. Then the probable values of M are plus 1, 0 and minus 1. Based on the above relations marked here, these three relations, it can be shown that L is numerically equal to total angular momentum. L is numerically equal to under root S cross. We can arrive at L cos theta is equal to Ms cross because Lz is equal to L cos theta, Lz is equal to Ms cross. Based on that, we can write, we previously know two relations, Lz is equal to L cos theta and also Lz is equal to Ms cross. Taking right hand side and equate it together, we will get this relation. Capital L cos theta is equal to Ms cross. Thus, root 2 S cross cos theta equal to Ms cross. S cross vanishes and M is equal to plus 1, 0 or minus 1. This leads to three different possible angles based on cos theta. That is, if M is equal to plus 1 is equal to root 2 cos theta. That implies theta is equal to cos inverse 1 by root 2. Cos inverse 1 by root 2 is equal to 45 degree. Now I am putting the second value for M, that is 0. 0 is equal to root 2 cos theta. That implies theta equal to cos inverse 0 by root 2. And this is the next angle, that is 90 degree. Finally, M can have one more value, that is equal to minus 1. So minus 1 is equal to root 2 cos theta. That implies theta is equal to cos inverse minus 1 by root 2 and that is equal to 135 degree. So, when L is equal to 1, M can have three values, plus 1, 0 and minus 1. This leads to the arrangement of angular momentum in three possible angles. They are 45 degree, 90 degree and 135 degree. This is the pictorial representation of the arrangement of the components of angular momentum when Lz is equal to 1. So, the angular momentum components are represented in three different angles, namely the 45 degree, 90 degree and 135 degree. This is the arrangement for L is equal to 1. Now, the second significance of magnetic quantum number, that is the Swayam effect. In the absence of a magnetic field, each energy level has a degeneracy that is equal to 2L plus 1. In the presence of a magnetic field, these 2L plus 1 levels split and energy depends on the particular value of M. The splitting up of energy levels, that is 2L plus 1 degenerate energy levels into different components under the influence of an applied magnetic field is termed as the Swayam effect. This is the pictorial representation of Swayam effect. Here we are representing a transition from 2p state to 1s state. And this transition is in the absence of the magnetic field. That means I am putting no magnetic field here. So I will get one and only spectral line. So in the presence of a magnetic field, this 2p level splitted into 3 levels. For P sub shell L is equal to 1. So 2L plus 1. 2L plus 1 means 3. The 3 possible levels corresponds to 3 magnetic quantum number values, namely plus 1, 0 and minus 1. So the 2p level splitted into 2L plus 1 levels, each level being non-degenerate. So we are getting 3 levels here. So this single transition splitted into 3 transitions. That means in the presence of the magnetic field, this one single line appears as 3 lines in the spectrum. Hence, the spectral lines splitted into 3 in the presence of the magnetic field for this transition. Hence, it can be concluded that the spectral line is splitted in the presence of the magnetic field, and this effect is termed as the Swayam effect. Now, first few real hydrogen-like wave functions. We know the complete wave function of the hydrogen psi Lm r theta phi. That is equal to theta of theta into r of r into phi of phi. So, whenever I am putting different values for n, l and m, we will get different values for hydrogen-like wave functions. And here I am representing only real values, and these are real hydrogen-like wave functions, and this corresponds to oneness. Oneness means, oneness orbital means, for that n is equal to 1, that is principal quantum number is equal to 1, azimuthal quantum number L is equal to 0, and magnetic quantum number m also equal to 0. That represents the oneness orbital. So the real hydrogen-like wave function corresponds to oneness orbital is 1 by root of pi, that is 1 by pi raised to 1 by 2 into z by a raised to 3 by 2 into e raised to minus zr by a. This represents the 2s orbital, and the wave function, the real hydrogen-like wave function for the 2s orbital is depicted here, and for this 2s orbital, we can put n is equal to 2, L again equal to 0 and m again equal to 0. Similarly, we will get arrangement for other orbitals also. 2pz, 2px, 2py and 3s arrangements are shown here. These are real hydrogen-like wave functions and not incorporated the imaginary part. These are first few real hydrogen-like wave function corresponds to different orbitals. Now, radial part of the wave function. The complete hydrogen atomic wave function depend on 3 variables, namely r, theta and phi. Hence, plotting or displaying them completely is very difficult. The radial and angular part are commonly considered separately. For brevity and simplicity, we consider real part as radial part and angular part separately. Now, radial part of the wave function, RNLR represents the variation of the wave function with the radial distance, that is small r, from the nucleus. We familiarized the variable r, that is the distance from the origin to the point P in the spherical polar coordinate arrangement, and the radial part of the wave function represents the variation of the wave function with the small r. The radial part of the wave function depends on 2 quantum numbers, namely the principal quantum number and the azimuthal quantum number. Now, consider that the space around the nucleus is divided into a very large number of thin concentric shells, each shell having thickness dr, which are at a distance r from the nucleus. Such concentric shells are shown in the figure. This is to mention about the radial distribution function. The volume of a spherical shell, of thickness dr can be denoted as dV. The volume of the spherical shell with the thickness dr can be denoted as dV. And that volume dV is theoretically equal to 4 pi r square dr. 4 pi r square dr. So, volume of the shell is 4 pi r square dr. dv is the volume of that small shell within radius r and r plus dr, and dv is equal to 4 pi r square dr. Now, radial distribution function is related to the probability of finding an electron at a distance between r and r plus dr from the nucleus to the hydrogen and hydrogen like system. Radial probability is represented as PR equal to RNLR square into dV. dV we already learned that volume of the small shell with the thickness dr. dV is numerically equal to 4 pi r square dr. Therefore, the probability, the radial probability function PR is equal to RNLR square multiplied with the 4 pi r square dr or dV. The plot of radial probability against R gives a set of curves known as radial probability distribution curves. So, what are radial probability distribution curves? The plot of radial probability against R. The plot of radial probability against small r is termed as radial probability distribution curve. And we are now moving on to the details of the radial probability distribution curve. This is the radial probability distribution curve for 1s orbital. And in the y-axis, I am taking the radial probability, and the z-axis represents small r, that is radius. And this is the radial probability distribution curve for a 2s orbital. Here in the y-axis, you can see the plotted parameter is the PR or radial probability. So, a plot of radial probability against radius is the radial probability distribution curve, we know it. And this is the radial probability distribution curve for a 2s orbital. And one important thing that should be mentioned here is that in the radial probability distribution curve, we can say some positions where the probability of finding an electron is equal to 0. See, at this portion, we can see the probability of finding an electron is equal to 0. The position, such a position are termed as radial node. Radial nodes are the position where the probability of finding an electron is 0 if we are moving along the radial distance. Number of radial node can be calculated by using the expression radial node equal to n minus L minus 1, where n represents principal quantum number, L represents azimuthal quantum number, and 1 is a constant. So, we are taking 2s orbital. For 2s orbital, n is equal to 2, and for s subshell L is equal to 0. So, number of radial node is equal to 2 minus 0 minus 1 in the case of a 2s orbital. So, 2 minus 0 minus 1 is equal to 1. So, in the case of a 2s orbital, we can see the presence of one radial node. So, this is the radial node for 2s orbital. Similarly, we can plot radial probability distribution curve for a 3s, 3p and any other orbitals. For instance, now I am simply plotting the radial probability distribution curve for the 2p orbital. First of all, I have to find out the number of radial nodes. And number of radial node here is equal to again n minus L minus 1. For 2p orbital, n is equal to 2, and for p subshell, L is equal to 1, and again we have to subtract 1. So, 2 minus 1 minus 1, that is equal to 0. So, in the 2p orbital, there is no radial node, and the curve appears to be like this. This is the nature of the curve. Here there is radial probability PR, and it is plotted against a radius. So, the curve appears like this, and here you cannot see the presence of the radial node. Similarly, we can plot radial probability distribution curves for other orbitals also. For example, I am plotting one more thing, that is the case of the 3s orbital. So, first of all, we have to find out the number of radial node. N is equal to 3, L is equal to 0. So, 3 minus 0 minus 1, that is equal to 2. So, in the case of the 3s orbital, we can see the presence of 2 radial node. and the nature of the radial probability distribution curve is like this. Here there is a PR and here there is R. This is the nature of the curve. This is one node, this is the second node, and this is the first one, second node. So here you can see the presence of two radial nodes in the case of the 3s orbital. That all about the case of the radial probability distribution curves. Now, the radial probability distribution curves will give certain conclusions. Radial probability is 0 at the nucleus. There is a principal maximum in each of the plot. That is, there is a probability maxima corresponds to each of the curve. As the value of n increases, the radius of the principal maximum increases. In the case of the 1s orbital, the principal maximum appears at 0.529 angstrom. That is simply termed as radius of the first orbit, or taken as A0 over the Bohr's radius. And next part of our discussion is angular part of the wave function. It is denoted as psi Lm theta phi. It depends on two quantum numbers L and M. The angular function depends only on the direction and is independent of the distance from the nucleus, that is small r. So, it is independent on r and dependent on two variables. They are angular variables theta and phi. Now, polar diagrams. A common way to represent angular function or spherical harmonics in three-dimensional figure is known as polar plot or polar diagram. Polar plot represents the value of angular wave function in any direction specified by the angles theta and phi. The shape and orientation of an atomic orbital are largely determined by the angular function. But the shape are not essentially angular functions. We have to include radial function also. Radial probability and angular probability collectively shown in the case of orbitals. And here we are telling about the representation of angular function only, and they are doing as the polar diagrams or polar plots. Now, polar plots for s orbital, that is L is equal to 0. S orbitals are spherically symmetrical and there is no dependence of the wave function and angle. So, this is the spherical polar plot for s orbital. Moving on to polar plot for p orbital. There are three possible arrangements. P orbitals are triply degenerate. This about the polar diagrams or polar plots corresponds to p orbital. This represents px, this one corresponds to py, and the final one corresponds to pz. The last one represents arrangement that corresponds to L is equal to 0, L is equal to 2 or d subshell. Here there are 5 possibilities, 5 possible arrangements. So, 5 sketches of the polar plots are shown here, corresponds to dxy, dxz, dyz, d square y square and dz square orbitals. These are about the polar plots. The shape of atomic orbital. A full representation of the probability of finding an electron requires total wave function in square and includes both the radial part as well as angular part. That is, the shape of the orbital is a cumulative plot of radial probability and angular probability. It needs a three-dimensional model to display the complete probability, and it leads to the shape of orbitals. That all about the present module. Thank you.